Today, we tackle a sorting challenge. Given an array of integers, how do you rearrange it based on the occurrence count of each number? Not just that, but if counts are equal, there's a specific tie-breaking rule. Think you can build an efficient custom sort. The problem, sort array by increasing frequency, asks us to sort an input array of integers. The primary sorting criterion is the frequency of each number. Numbers with lower frequencies should come before numbers with higher frequencies. As a secondary rule, if two numbers have the same frequency, they should be sorted in descending order of their actual value. The output is the sorted array. A naive approach would be to convert our array into a mutable list and then use a custom sort function. Inside this custom sort, for every pair of elements being compared, we'd iterate through the asterisk entire original array to calculate their frequencies on the fly. This repeated frequency calculation for every comparison is incredibly inefficient. If the list has n elements, and each comparison takes n time to find frequencies, the sort itself, which is typically n log n, becomes n squared log, and this redundant work makes it too slow, even though space complexity would be linear for the list. The key insight for optimization is to avoid recalculating frequencies repeatedly. We can pre-compute all frequencies once. We'll use a HashMap to store each number and its corresponding frequency. Iterate through the input array, and for each number, increment its count in the map. After this single pass, our HashMap holds all the frequency information. Now, we convert the original array into a list, similar to the brute force. But this time, when we apply our custom sort, our comparison logic can simply look up the frequencies in our pre-populated HashMap. This lookup is an average constant time operation, so our custom sort now performs much better. The comparison function will first check if frequencies differ. If they do, sort by frequency ascending. If frequencies are the same, it then sorts by the number's value in descending order. Finally, convert the sorted list back to an array. Let's trace this with the example array, 1, 1, 2, 2, 2, 3. First, we build our frequency map. 1 appears twice, 2 appears 3 times, and 3 appears once. So our map is 1 maps to 2, 2 maps to 3, 3 maps to 1. Next, we convert the original array into a list. Now we sort this list using our custom comparison. When comparing 3 and 1, 3 has frequency 1, 1 has frequency 2. Since 1 is less than 2, 3 comes before 1. When comparing 2 and 1, 2 has frequency 3, 1 has frequency 2. 2 comes after 1. Consider two 2's, both have frequency 3. The tiebreaker rule applies, sort by value descending. So a 2 remains before another 2. After all comparisons, the list becomes 3, 1, 1, 2, 2, 2. The final result for the input 1, 1, 2, 2, 2, 3 is 3, 1, 1, 2, 2, 2. This is correct because 3 has the lowest frequency of 1, followed by 1 with frequency 2, and then 2 with frequency 3. The 2 1's and 3 2's maintain their relative order by value. You'll spot this pattern when a problem requires sorting based on some derived property of elements, like frequency, or when there's a multi-level sorting criteria. The signal is usually an array or list that needs a specific, non-default ordering, often coupled with a need to count or categorize elements first. Time complexity is big O of n log n, linearithmic time due to the sort operation, as map lookups are constant time on average. Space complexity is big O of n for both the frequency map and the list used for sorting. This technique of pre-calculating values for custom sorts is widely applicable. Try the next problem involving custom sorting for more practice. Same pattern. Don't forget to like and subscribe for more DSA insights.